In the previous video, we concluded our discussion on electron configuration. Today, we will try and close out Unit 1 by revisiting a concept that we mentioned very briefly earlier. In Unit 1, Video 1, the first video of this series apart from the introduction, we began looking at the periodic table to try and figure out all the different pieces of information it can give us. We looked at atomic number, element symbols, and one parameter that we haven't really talked about since, the atomic weight. Previously, we defined the atomic weight as an approximate measure of the mass of an atom. This was enough of an explanation at the time, but the purpose of this video is to elucidate a bit more on what exactly atomic weight is, and how it relates to isotopes, which are another important and as yet undiscussed feature of atoms from the same element. Let's begin by reviewing a bit from Unit 1, Video 1. We know that atoms are the tiny particles which comprise all matter. We also know that atoms with the same atomic number are classified into elements, and there are currently 118 known chemical elements. Atomic number, remember, is nothing more than the number of protons, and in ordinary atoms, the number of protons is equal to the number of electrons. To reiterate, the number of protons is what ultimately determines which element a particular atom belongs to. The overarching implication of this is that the number of protons in an atom must stay constant. If an oxygen atom, which has 8 protons, were to somehow lose a proton, it would no longer be an atom of oxygen. An atom's number of protons is what determines which element it belongs to. But what about the other subatomic particles? Are they constant? We already know that the number of electrons is not constant, since the formation of ionic bonds necessitates the giving of electrons from one atom to another. Once an ionic bond forms, one atom has fewer electrons than it started with, whereas the other atom has more electrons than it started with. So the number of protons is constant, the number of electrons is not constant. What about neutrons? Does the number of neutrons in an atom ever change? The answer is yes. Some atoms have the same number of protons but a different number of neutrons, and these atoms are referred to as isotopes. Remember, isotopes belong to the same element. Always. We can't overstate this point. Isotopes belong to the same element and therefore have the same atomic number. The only difference between two isotopes of carbon, for example, is a difference in their masses. This makes sense if we take a moment and think about it. Neutrons have a measurable mass, so a carbon atom that has one fewer neutron will have a lower mass than a carbon atom that has one more neutron. We can get this by looking at the word isotope itself. The prefix iso comes from the Greek word isos, which means equal. Equal number of protons, same atomic number, same element. Let's not forget that. Now, how do we name isotopes if they belong to the same element? The easiest way is to simply append the isotope's mass number after the name of the element with a hyphen in between. For instance, the isotope of carbon with a mass number of 14 is denoted as carbon-14. The isotope of carbon with a mass number of 13 is written as carbon-13. Again, both these isotopes are carbon because both have 6 protons. Mass number, by the way, is equal to the number of protons plus the number of neutrons in an atom. Let's immediately jump into an example problem to apply this concept. How many neutrons are there in an atom of carbon-14? We've just established that the nomenclature for isotopes involves appending the mass number after the element name with a hyphen in between. In this example, carbon is the element name. So 14 must be the mass number. Mass number is equal to number of protons plus number of neutrons. We can quickly find the number of protons by glancing at a periodic table. And because carbon has an atomic number of 6, this isotope must have 6 protons. With a bit of quick subtraction, we find that carbon-14 has 14 minus 6 neutrons, or 8 neutrons in total. There are, however, two alternative ways to show isotopes. These are by no means the official names for these notations, but I like to think of them as the superscript and subscript notation versus the superscript only notation. The first of these, the superscript and subscript notation, is quite simple. All we need is the element symbol and two numbers. We first write the element symbol. The example here is carbon, so the element symbol is an uppercase C. Then, we add the mass number as a superscript and the atomic number as a subscript on the left-hand side of the element symbol. 14 is the mass number, so we write it in the top left, and 6 is the atomic number, so we write it in the bottom left. Remember, mass number always goes in the superscript, and atomic number is always in the subscript. A good way to remember this is to remember that mass number is always going to be larger than atomic number, and because of this, the mass number deserves to be in the superscript. The superscript is always going to hold the superior or larger number. Our second alternative method is, if anything, even simpler. All we need for this notation is the element symbol and the mass number as the superscript. We can omit the atomic number entirely and write carbon-14 as an uppercase letter C with the number 14 in its top left-hand corner. In all honesty, this second alternative notation is very common, mostly because there really isn't a need to write the atomic number for an isotope, because we should know the atomic number just by looking at the element symbol, since the atomic number for an element never changes. I'm sorry to harp on this point so much, but it's very important that we start thinking of isotopes as variations of an element instead of as divergent chemical substances. When it comes to pronouncing isotope names out loud, it should be noted that we always pronounce isotopes as element name followed by mass number. Carbon-14 is therefore always pronounced as carbon-14, regardless of how it is written on paper. One common question regarding isotopes is to ask why isotopes exist at all. Where did they come from? We can't give a complete answer to this at the moment, but the basic idea is that the existence of isotopes has to do with radiation. Some radioactive atoms can lose subatomic particles, including neutrons, by emitting them as radioactive particles in the forms of alpha, beta, and gamma radiation. We will discuss particle radiation in detail in Unit 10 when we arrive at nuclear chemistry. Alright then. Now that we've introduced isotopes, we can begin talking about today's main topic, atomic weight. If we remember from our initial look at the periodic table, we saw that the periodic table's squares contain a number, usually a decimal number, that we called the atomic weight. The reason we didn't talk about atomic weight in greater detail then is because it's sort of a complex topic, as we'll see in a minute. Which seems a bit odd, considering it seems like such a simple concept. The primary reason for this complexity is because of the terminology. In all seriousness, the terminology surrounding atomic weight is actually a major controversy in chemistry, and depending on which sources a person reads, they'll have a completely different idea as to what some of the terms we're going to look at today actually mean. I didn't want to scare anyone away by throwing 20 different technical terms and a dozen different acronyms on the screen in a single video, which is why I've decided to save this content for the last video of Unit 1, rather than the first video of Unit 1. I've tried explaining everything as thoroughly as possible to help prevent confusion, but I would honestly recommend taking thorough notes as we move through this section, since there's only so much simplification we can do before we start cutting into the important topics. I also apologize in advance if this video goes a little long for the same reason. Feel free to skip sections if it feels as though we're traveling over the same ground over and over again. Our first confusion arises almost immediately when we try to define atomic weight. The most common definition of atomic weight is the ratio of the average masses of all the isotopes of an element to a constant value. This definition of atomic weight is also called the relative atomic mass, or RAM. The key feature of relative atomic mass is that it applies only to a specific sample of atoms. Fossils, for instance, are composed mainly of carbon because bones are composed mainly of carbon. Carbon has several isotopes, and these isotopes all have different masses because they have different numbers of neutrons. Let's suppose we have two fossils, each taken from a different location. One fossil might be made up of mostly a heavier isotope of carbon, that is, a carbon isotope with a higher mass number. The second fossil, on the other hand, is made up of a carbon isotope with a lower mass number. Depending on which fossil we use as our sample when calculating relative atomic mass, we're going to get different average values. If this doesn't make much sense now, we'll explain it a little more later on. Mathematically speaking, the relative atomic mass is equal to the average masses of the isotopes in a sample divided by a constant value. The constant value is something called the atomic mass constant, and the atomic mass constant is equal to exactly 1/12 the mass of a carbon-12 atom. So, relative atomic mass is equal to the average masses of isotopes in a sample divided by 1/12 the mass of a carbon-12 atom, as denoted here. Now, point 12 is where the confusion really starts to come in. The term atomic weight can also be used to represent a parameter called the standard atomic weight, or SAW. Standard atomic weight is a value for each element published by an organization called the IUPAC, which stands for International Union of Pure and Applied Chemistry. The IUPAC is currently headquartered at the Research Triangle in North Carolina, and it is one of the largest organizations involved in the advancement and standardization of the chemical sciences. The IUPAC sets a lot of official standards in chemistry, like establishing a standard nomenclature for compounds and such, but another major standard they set is the standard atomic weights for each element. Essentially, the way this works is, the scientists at IUPAC take a large number of samples from all over the world and analyze these naturally occurring samples for different elements. If they're doing an analysis for carbon, for example, they will analyze each of these samples and try to determine how much carbon is present. Once they find that, they then try to find the isotopic composition, or in other words, they try to see how much of each isotope of carbon is present in that sample. The IUPAC scientists will repeat this procedure for all the samples they have, and use those values to calculate a relative atomic mass that any chemist living anywhere in the world can use. Standard atomic weight, then, is basically a value for relative atomic mass that could theoretically be applied to any sample found anywhere on Earth. The key word here is theoretically. There will be some discrepancies, obviously, but the purpose of publishing standard atomic weights for each element is to provide a standardized and statistically accurate value for relative atomic weight, so scientists in different parts of the world aren't using completely different values for an element's relative atomic mass. We've already answered this a little bit, but the question has to be asked. Why do we have both relative atomic mass and standard atomic weight? The primary reason is because of the naturally occurring variance in RAM values. A sample of carbon taken from a fossil found in France might be made up of 70% carbon-14 and 30% carbon-13, while a sample taken from a fossil found in the United States might be made up of 90% carbon-14 and 10% carbon-13. The sample taken from France is going to have a different relative atomic mass than the sample taken from the United States, because the isotopic composition is different. This is what makes the relative atomic mass a relatively unreliable parameter. Of course, standard atomic weight isn't perfect either, but it does serve as a reliable and well-tested value for chemists anywhere in the world. Again, the confusion we have to avoid here comes in because both relative atomic mass and standard atomic weight are called atomic weight. Now, a person might be tempted to ask why that's the case, and the answer there is because both RAM and SAW values can be found on the periodic table. Why is this the case? The reason this is the case is because it's not possible to find a true standard atomic weight for some elements, especially radioactive elements that disappear very quickly and are very difficult and expensive to make in a lab. The IUPAC releases values for these unstable elements as well, but it isn't feasible to take many different samples and find a real standard atomic weight. When this happens, the relative atomic mass from a few samples is used instead. Out of the 118 known elements, 84 of them have a standard atomic weight available, and the remaining 34 do not. Finding the relative atomic mass involves averaging the masses of isotopes. The mass of one atom of a single isotope, however, is simply called atomic mass. Now, most of the actual mass of an atom, and by this we mean how much stuff an atom is made up of, is actually found in the protons and neutrons. Electrons do have mass. We can't necessarily assume that they don't, but when compared to protons and neutrons, their mass is negligible. Just to give an idea as to how small an electron is, if you take the mass of a single proton and divide it by 2,000, you'll get the mass of an electron. In other words, we would need to pack together 2,000 electrons in order to make a particle the same size as a proton. The true mass of a single electron is so measly that we essentially just ignore them when talking about atomic mass. The practical implication of this is that the atomic mass is roughly equal to the mass number. Again, mass number is equal to the number of protons plus the number of neutrons. Electrons have such a small mass that they are often represented as decimal values, with the whole numbers serving as the combined protons and neutrons. We also need to talk about the units for our before-mentioned parameters. There are two units of the atomic mass, the Dalton, abbreviated dA, and the Unified Atomic Mass Unit, abbreviated U. Both of these units are defined as the mass of a carbon-12 atom divided by 12, or 1/12 the mass of a carbon-12 atom. This means that 1 Dalton is equal to 1 unified atomic mass unit, which is equal to the atomic mass constant. Let's do another example problem. Example 2 says, what are the units of RAM and SAW? Feel free to pause the video if you'd like to figure this one out for yourself. This is actually a trick question because the units of RAM and SAW don't actually exist. If we move up a bit and look at our definition of RAM, give me one moment here. Right here, we will see that the RAM is equal to the average masses of isotopes divided by 1/12 the mass of a carbon-12 atom. Now, both the masses of isotopes, which these are the atomic masses, and 1/12 the mass of a carbon-12 atom are measured in Daltons, or in unified mass units. This means that trying to calculate the RAM involves dividing a parameter whose units are Daltons by another parameter whose units are also Daltons. In the end, both Daltons get cancelled out, which leaves the RAM as a unitless or dimensionless parameter. In other words, there are no units of RAM and SAW. That was a lot of confusingly overlapping terminology, wasn't it? Let's take a minute to review. Firstly, an isotope is an atom of the same element but with a different number of neutrons and therefore a different mass. Secondly, the mass number is the number of protons plus the number of neutrons. Thirdly, the atomic mass is the mass of protons plus the mass of neutrons plus the mass of electrons in an atom, and it is measured in either Daltons or unified atomic mass units. Remember, mass number and atomic mass are almost equal. Fourthly, the atomic mass constant is equal to the mass of one carbon-12 atom divided by 12. Fifthly, the relative atomic mass is the average atomic mass of all an element's isotopes in a single sample divided by the atomic mass constant. Sixthly and finally, the standard atomic weight is a value of the relative atomic mass of an element that is determined by the International Union of Pure and Applied Chemistry. The IUPAC calculates the standard atomic weight by taking many samples from nature and determining the relative atomic weights from all of them. One final point. 1 Dalton is equal to 1 unified atomic mass unit, which is equal to the atomic mass constant, which is in turn equal to 1/12 the mass of a single carbon-12 atom. Here's another example problem. Example 3 asks, what is the atomic mass of carbon-12 in daltons? Remember, 1 dalton is equal to the atomic mass of a carbon-12 atom divided by 12. So we end up with this equation. If we solve for the blank value here, we find that the total atomic mass of a carbon-12 atom is exactly 12 daltons. Here's another common question about atomic weight. Why exactly do we use 1/12 the mass of a carbon-12 atom for the atomic mass constant and the dalton, as well as the unified atomic mass unit? This is a great question, by the way, because it does seem a rather arbitrary value. Why don't we use the total mass of a carbon-12 atom, or any other atom for that matter? Believe it or not, there is a logical explanation for this, a method to the madness. As an isotope of carbon, carbon-12 has 6 protons, and because of its mass number of 12, it also has 6 neutrons. Even more amazingly, it even has 6 electrons. Carbon-12 has equal numbers of all 3 subatomic particles. Now, electrons have negligible mass, and because 1 dalton is equal to 1/12 the mass of a carbon-12 atom, it logically follows that 1 proton or neutron has the same mass as 1 dalton. Again, there are 6 neutrons and 6 protons in a carbon-12 atom, which means that 1 neutron or 1 proton has a mass of 1/12 the mass of a carbon-12 atom. 1/12 the mass of a carbon-12 atom is equal to 1 dalton. So the mass of 1 proton or neutron must be equal to 1 dalton. By defining a dalton the way we do, we allow the mass of 1 proton or neutron to equal 1. This is what makes the atomic mass roughly equal to the mass number, which goes a long way in making our lives easier. One final note about isotopes. Because isotopes belong to the same element, they have similar chemical properties. Isotopes react in the same way and form bonds in the same way. The practical differences between different isotopes of the same element lies in their physical properties. The atomic mass helps determine a substance's melting point, boiling point, density, and other physical properties, so these parameters are going to vary between isotopes. A good place to end this video is with a discussion of some common types of problems associated with isotopes. There are 2 main problems many general chemistry courses will ask regarding isotopes. Either they will ask us to determine the number of subatomic particles in an isotope, or they will ask us to calculate the average mass of several isotopes. The average mass of several isotopes, remember, is how we get the numerator term when calculating the relative atomic mass. I could go on talking about these types of problems, but the most efficient way to demonstrate the concepts involved is by working through some examples. This video will provide 2 examples of each of the problem types discussed earlier, so 4 examples in total. Let's start with example 4, which says, state how many protons, neutrons, and electrons are in a single atom of nitrogen-15. You can pause the video here and try this for yourself, or we can work through it together. Our first step is to find the atomic number of nitrogen. Which is 7. The reason we find this value first is because atomic number gives us the number of protons, and the number of protons of an element never changes. atomic number is equal to the number of protons. And just like that, we're a third of the way done. Now, because this is an atom and not an ion, the number of electrons has to equal the number of protons. So nitrogen 15 must have 7 electrons. Finally, to find the number of neutrons, all we have to do is subtract the atomic number from the mass number, or 15 minus 7, which yields 8. And that's all there is to it. Next one. Example 5 would like us to repeat example 4, but for a single atom of uranium-234. The atomic number of uranium is 92. So we have 92 protons. Again, this is not an ion, so we also have 92 electrons. To find the number of neutrons, we subtract 92 from 234. To get 142 neutrons. These next two examples are a bit more complicated. Example 6 says, calculate the weighted average atomic mass of the following 3 isotopes of silicon, or Si, given the data. As a quick aside, the weighted atomic mass is the same thing as the averages of all the isotopes. It's just the more technically accurate name. So let's look at these 3 silicon isotopes. The data here gives us the atomic masses of these isotopes in daltons, and it also gives us these percentage values. These percentage values are called the abundances of the isotopes in question, which is essentially an estimate as to how much of these isotopes can be found in the Earth's crust. The first isotope, silicon-28, has an abundance of 92.18%, which means that of all the silicon in Earth's crust, 92.18% of it is in the form of silicon-28. Silicon-28 has an atomic mass of 27.98 daltons. Next, we have silicon-29, with an atomic mass of 28.98 daltons and an abundance of 4.17%. And finally, silicon-30, which has a mass of 29.98 daltons and an abundance of 3.12%. We haven't talked about how to solve this type of problem yet, so I would recommend watching as we work through this one together. Finding the weighted average atomic mass for multiple isotopes involves the following formula. We need to multiply each isotope's atomic mass by its abundance and then add all the combined values together to find the weighted average. Let's do that now. Remember, we have to convert the abundance values from percents to decimals before we can start multiplying. Don't rush through these and multiply percentages by whole numbers. It never leads anywhere good. There we are. Now, all we have to do is do some math, and once we do so, we'll find that the weighted average atomic mass according to these data is approximately 28.09 daltons. Your answer might differ a little bit based on the rounding you do, but it should be relatively close. Last example problem. Example 7 gives us all these data. The weighted average atomic mass of iron, it says, is 55.85 daltons. Iron has 4 main isotopes. Iron 54 has an atomic mass of 53.94 unified atomic mass units and an abundance of 5.85%. Iron 56 has an atomic mass of 55.93. I think I'm just going to use the abbreviation from here on up. It has an atomic mass of 55.93 U and an abundance of 91.75%. We aren't given the atomic mass of iron 57, but we know that its abundance is 2.12%. Finally, iron 58 has an atomic mass of 57.93 U and an abundance of 0.28%. What this problem wants us to do is find the approximate atomic mass of iron 57 given these values. Feel free to pause the video if you'd like to try this one yourself. This one might look a little complicated, but all we're doing is adding a tiny bit of algebra into the mix. We have the weighted average atomic mass, so we can put that over here. We also have all the abundances and all but one of the atomic masses, so we write all those values on the opposite side of the equal sign, and leave the variable y to equal the unknown value, which is the atomic mass of iron 57. Then, all we need to do is divide the weighted average on the left by all these values on the right exclusive of variable y. Doing this eliminates all the terms on the right-hand side of the equation and leaves y to equal approximately 55.85. And the unit, of course, is the unified atomic mass unit, or U. We could just as easily use Daltons, of course, but it's good practice to be consistent with the units used by the problem statement. That concludes Unit 1 covering atoms and molecules. In the next video, we will begin Unit 2, which is entitled Molecular Geometry. Unit 2, Video 1, will cover ionic bonding. Thank you for watching.